Hello everyone, this is teacher Tumsi Metoni, a teacher of physics and mathematics, both O and A level. Today we are going to talk about the derivation of speed of sound in air. We know sound is a wave, and for it to propagate, it has to have a certain media, and that media can be solids, liquids, or gases. So it has different velocities through these different medias. So specifically for speed of sound in air is always given by this formula, which is the square root of, this is gamma, which is the adiabatic index. This is R, the gas constant. Tk, it is the absolute temperature. It means that it has to be in kelvins. And M is the molecular mass. So we are going to go through a different steps of how we can come up with that formula. And we are going to do some few examples and see. So now we begin. First of all, we consider a fluid flow in a pipe of cross-sectional area A. So if this is our pipe, and we know it has a cross-sectional area A, and a fluid is flowing through, or a fluid can be air. Talk about air specifically. So now air is flowing through this pipe. So we are concerned about, let us now consider if that air is flowing through a length x, through that pipe. So we know that the volume, you can say the volume of that air, the volume of air in length x, we know that volume is equal to the cross-sectional area times the length. But specifically today, we are going to be concerned about that mass of that air that is flowing through this length x. So the mass in the volume of length x, mass is given by, we know that mass is density times volume, so it is the density of that air times the volume, which is the density times the area times x, which is rho A x. So now we have that equation that the mass of that air flowing through that length x is rho AX. So now what are we considering next? Now we are going to consider the mass flow rate, the rate at which that mass is flowing through that pipe. We can call it the mass flow rate. The M, the T is equal to D rho A X dt, which is the density is constant and the area is constant. So we can push them back, since this differential thing is linear. So it is rho A dx dt. And from our mechanics, we know that the rate of change of displacement is a velocity. So now we have rho A v. So I'm going to try to write my velocity like this in order to differentiate it with the volume v. So this is the velocity. maybe I can indicate it that it is the velocity. So we have the mdt is equal to rho a v. So what are we going to talk about next? We know that from the continuity equation, if we have, let's say if we have, I'm going to wrap this, but in case we need it, you can go back in the video, but I'm going to explain this using that. So from the continuity equation, if we have this value flowing in, it is the same value that is flowing out, i.e. what do I mean? That the density inside entering into the tube and the area inside and the velocity inside entering, it will be equal to this hole entering into the pipe. It will be the same when it is getting out. I.e. what we mean that rho AV is equal to a constant, So now rho AV is equal to a constant. So this one is going to help us in our next step. So that's all we can talk about that fluid or that air flowing through that pipe. So now maybe I can call this step 1. Then step 2, then consider an air parcel. Consider an air parcel through which a sound wave travels. What is an air parcel? So an air parcel, we can call it a small volume in air. Since we are dealing with an air parcel, it is a small volume with imaginary boundaries. We just take a small volume in air with imaginary boundaries. Suppose this is my air parcel. I'm trying to take that imaginary volume, imaginary boundaries. So this is my cube. So what am I interested in? Suppose now a sound wave travels through that air parcel. What will happen? We have, first of all, what we have the density of that sound wave entering into this air parcel, and we also have it is traveling at a certain velocity. I told you I'm going to use this V to denote velocity. You can use any other figure or any other symbol, because I want to differentiate it with volume. Don't confuse the two. So now it is at a certain velocity and certain temperature. So now we are going to suppose that it is entering at a certain density and it is moving out when the density has changed a small amount, say the rho, and velocity has also changed to the V, and the temperature has also changed to the T. So all we need to talk about here is relate this to the continuity equation. We know that rho AV is a constant. This implies that rho times area, let's say this face has a cross-sectional area A, or we can imagine that these boundaries are, maybe this is the Y, this is the X, and this is the Z. This is the Y, the same from a cube. Those are the imaginary boundaries. Yeah. So our row A, V, this is the one that is entering, is the same as the one that is moving out. Our row has changed to the row. The area is still the same because the area of this face is the same area. The area of this face here is the same area of that face. So now we have V velocity plus dv. So on solving this, we shall have rho av is equal to, this times this is rho v plus rho dv plus, remember our area is cancelling out, so this is rho dv plus v d rho. So we see that since our area has gone out, we don't need it here. So we have something like rho v, like that, is equal to that. So which implies that we have our rho dv is equal to v d rho. So we shall need this equation as we go ahead. So that is what we needed from there. So the next thing, before I rub off, we are going to talk about the net force. The net force of that, because when this sound is being propagated through that, it exerts a force here and here. So we shall get the net force. We know the force. We know how force is related to pressure. Remember that. We know how force is related to pressure by P times A. So we are trying to bring in the element of pressure because our equation here has something like RT. We know that PV is equal to nRT. So that is what we are trying to build up. And we know how are we going to get rid of the force. We know that the force is mass times acceleration. So we are getting the mass, changing it into volume, density and volume. Sorry, V. Density and volume, and acceleration. We shall also deal with it because we know acceleration is dv dt. So that's how we are going to get rid of all these things and relate to our equation and come up with something like that. So maybe I can rub. So we have had our diagram. Like this, where we had something entering and something leaving out. This is the cross-sectional area A. We had dy, dx. This is dz. So now we say that the volume is changing to a certain figure and temperature and also the velocity. So V, rho, and T. So we are going to talk about the net force. The net force on the air parcel F is equal to pressure. Suppose now the pressure here is P, and the one that is moving out is dP, is P plus dP. So we have P times the area. We see that the area here is dy dz. the area of this shaded face is simply the length times the width. So it is P dy dz. Then minus the pressure, okay, the net force. So maybe you can call this F in, and what we write here is F out. How do we get that one? Because we see that it is P. So now the pressure that is moving out is P plus dP. It is also changing to a small amount dP. So we have P plus dP like this. Then it is moving out through that cross-sectional area, which is the same. This is dy and this is dz. So this is dy dz. Remember, previously we have had our equation somewhere that v d rho is equal to minus rho dv, which we got from the continuity. We say this equation is going to be so much important for us. So we see that our force is mass times acceleration is equal to, this is P dy dz minus, this is P dy dz plus, no, this is minus dP dy dz. So now we have our mass times acceleration giving us minus dP dy dz, because this one will cancel with that one because they are the same. We don't need them anymore. So the mass, we know that mass is equal to density times volume V. So we have density times volume. Remember, this is acceleration due to gravity. So now it is given by dv dt. So we are going to replace it with dv dt. This is the same as rho, no, this is minus dp dy dz, like that. So this is volume, the volume of this air parcel, we know it. The volume of a cuboid, it is dy dx dz. So this is dy dx dz, dy dx dz, rho dy dx dz dv dt. This is minus dp dy dz. From here, what are you seeing? Are you seeing that dy dz, they are going away, and we are remaining with something like rho dx dv dt. So we have rho dx dv dt is equal to minus dp, like that. So mathematically, I can choose to remove this dt and put it here, and it has no problem. So you see that I'm trying to get rid of things I don't want, because I want to relate this with my equation. So I have to remain with things I want. So now here I have dv. So I know the x dt is, we know that velocity is equal to the x dt. We have seen that earlier. So I can say, where I have the x dt, I replace it with volume equal to minus dp. I call this equation. So I get, now what I do, I get this equation where I have the p, where I have, I combine these two equations. For example, I can say, I can make dv the subject of the formula, and where I have dv there, I substitute it. So this is just simple substitution. So I have my dv is equal to minus dp over rho v. So I can call these equations. Then I say put in that equation here star. So I have v the rho is equal to minus rho the v is dp. Because of this minus, this will become a plus, so dp over rho v. So I see that this is cancelling with this. So I have, take this v, I have v squared is equal to dp over the rho. So I have my velocity as the square root of dp over the rho. So this is a very important equation. I can name it, say, Roman 1, because I'm seeing light at the end of the tunnel. Once I get this square root, so I can just simply, we are remaining with only one assumption that is going to lead us to this. So I have something like pressure, you see that, have density, and I have something like molecular mass. So you can see that we are soon arriving to the right answer. So from here, note, take this note serious, and it is very important. When the sound is traveling through this air parcel, there is no heat is added. Let me write it. When sound is traveling through the air parcel, no heat is added or removed. So what does it mean? It implies that it is a diabatic process. So now, so it is a diabatic process. What does that mean? We know that a diabatic process, for a diabatic process, PV times the adiabatic index, which is gamma, that we'll talk about, is equal to constant. So we start from there. I'm going to rub off, but if you need some information here, you're going to go back and replay the video, and you'll be able to find everything that you need. So now the equation I want, I'm going to deal with, we know it, that V is equal to dP over the rho. So I can write it here in the corner that we have got that V is equal to the square root of dP over the rho. But we have said it is a diabatic process, so we say PV is equal to the constant. Remember that this V is volume, so this implies that P, but volume is mass over density, like this. This is a constant. So this is P. I can say that this is a constant. Why? Because I'm going to get from here, let me explain. I'm going to get P times m power this over rho power this. The mass is constant, so if I power it to anything is a constant, then I can divide it here. I still remain with a constant. So I have something like this. So that's the small technique there. So now here I have this is equal to a constant. So I have P over rho power this, the adiabatic index is equal to constant. So now here, remember I have the P, the rho. So I can say from here, introduce natural logarithm. So I have ln P over rho like this is equal to a constant. So maybe let me try to divide here. So now I have ln this. So this one gives me ln P minus ln rho power this. But since it is a logarithm function, I can put my adiabatic index there, and it is equal to ln of a constant is a constant. Wow. Ln of a constant is a constant. So now from here I can differentiate with respect to P, because I need to create a dP somewhere. So now I will have that d ln P minus rho over dP. This is if I differentiate a constant with respect to P, the constant I have there. So now I have no. If I differentiate ln P, I get 1 over P like that. Then minus, this is a constant. If I differentiate this ln rho with dP, I'll get something like 1 over rho d rho dP. Like that. Yes, it is correct. And this one is equal to, if you differentiate a constant, you always get 0. So now I can do my things and say, decide to make my dP d rho the subject of the formula, such that whatever I get, I just substitute it in my formula. So now I have dP d rho is equal to, I take the other one, the other side, I will have what? What do I have? So it is 1 over P n times rho over that. So which is now okay. So the P d rho is that. So yes, which is that. So are we safe? So now here we having d rho dP, and we are making it dP d rho. So it means this will be the reciprocal. It will be the reciprocal. It will be now, I'm making dP d rho the subject. So from here, let us do it together. So we have d rho dP is equal to 1 over P. I will divide by this and multiply by rho like this. So if I want this is P, not d rho. So if I have the P d rho, because I want to make this, I will get this over this. So I have the P d rho as P times the index of a diabatic process over rho. So from here, I know that my PV is equal to nRT, where T is the absolute temperature. So it means that, this implies that my dP d rho is given by P. So from here, P is this over V. I divide both sides by V. So I have my P, which is nRTK over V. This is for P, then times rho times the index over rho, like that. So I know that from, how do I introduce this M? I know my N is equal to M over M. This is the molecular mass. So I substitute it here. I have something like M R T K. Is that right? M R T K over capital M, then V, then times the density, then times the index. So this gives us, we see, pay attention here, this is M over V. Mass over volume. What does it give us? It gives us density. Let me write it here. So we have mass over V. We consider it here. It gives us density. So it gives us density. So it means that I can comfortably cancel this, and this. Is that right? So such that I remain with RTK this over M. So this is RTK over M is our dP d rho. Then from there, I can comfortably substitute in my equation. I know, I say from V is equal to the square root of dP d rho. I'll have my V equal to the square root of RTK over the molecular mass. That is all we can talk about the velocity, and this is our equation that we wanted to derive. So what can we talk about this before we end the session? We see that the adiabatic index is a constant. We see that this is the gas constant. And this is also always known. We can always know this. So it means that the velocity of, or the speed of sound in air largely depends on the temperature. It means that when the temperatures are high outside there, sound travels very faster. Is that okay? So we can simply say that V in air is directly proportional to the absolute temperature. When the temperatures are high, sound will travel faster through air. And when the temperatures are low, will travel slower. So this is what it implies. So see you next time when we are going to derive the velocity of sound in solids. And we shall see that the velocity or the speed of sound in solids is much higher than when it is traveling through air. And we shall see the reasons why. Thank you so much. And please, if you find this video interesting for you, you can go ahead and subscribe to my channel and click on that notification button. Thank you guys. See you later. Bye.